That's how I get the frequent.
Okay, well, let's get started. Smaller group, but that's okay. We're gonna get down and dirty in the mud today. We're gonna learn what's inside Xilinx FPGAs. So Dr. Goders last time gave you a very nice high-level overview of sort of what an FPGA contains. And I saw the presentation, and towards the end, somebody made some reference to, oh yeah, in 220, we covered a lot of this. And the comment was made, well, you're going to need to see it multiple times before it sinks in. Did I get that right? Do you remember that comment? Yeah, and the same goes true for this. We're going to dive way down in, but we're still not going to get very deep. Okay, so I am going to focus on Xilinx 7 series FPGAs because that's what I have the most experience with over the years. I would say that within our group, what percentage of our work has been done using Xilinx versus others, Lattice and Altera?
Oh, not 97%.
Okay, that was the number I would choose.
80% 7 series or 70 or 80% 7.
Yeah, so it's the common one, and so it's the one we'll talk about. Okay. Now, one of the things you're going to notice is that I'm just going to be referring to Xilinx documentation the whole time. Think about it. An FPGA vendor makes chips that they advertise as being able to implement any circuit your heart desires. Does it make sense to you that they have a built-in motivation to make them as easy to use as possible so that you will use them and buy them and put them in your products? Yeah, sure. So unlike some things that we work with, they're very well documented to a certain level. But then when you get below that level, there's nothing, because that's the custom silicon implementation, and that's where the companies believe their secret sauce, proprietary information is. But in terms of the building blocks that you can interact with as a designer, they do everything they can to document them carefully. So you should never say, I don't have a clue how to do X on this FPGA. I guess I'm stuck, because there is documentation on that. So as we do this today, and those of you in the back might want to come forward, because I can make this as big as will fit on the screen, but there is going to be some limits to how big I can make it. And so your reading it may be challenging. So the first one I went to was what's called the 7 series datasheet. And notice up here, it says DS180 with a version number and a date. You do this a few times and you realize, okay, they have data sheets and they have user guides, or UGs. And the UGs are where we get most of our information. But they'll reuse the same number and they will update it to a new version. So if you find a UG 474 with a date of 2011 on it, you might want to look for a newer one. There's probably one from 2018 or 2017. Okay, all I wanted to show in this one is let's just go look at a typical family comparison and how they describe their families. So as we can see here, they say, well, let's look at Arctic 7. This is what we're interested in, the second column. And they say, okay, we have 215,000 logic cells. Who remembers what a logic cell or a logic element was from Dr. Goders' lecture? Anybody remember? Nobody? Okay, well, you weren't paying attention. I keyed into it because there's special terms that you'll key into when you start talking about an FPGA. Do you remember he showed a LUT flip-flop combination? Okay, and did you call it a logic element or logic cell?
Oh, the logic element.
Logic element, or LE for short. So here we go. A logic cell is kind of like a logic element. However, back in the day, they calculated it using a 4-input LUT and a flip-flop. Well, they now have twice as many flip-flops as LUTs, and the LUTs are 6-input. So it's hard to know what that 215,000 means. I have here in my notes the ratio between the number of logic cells and 6-input LUTs is 1.6 to 1. See, so they're continuing to quote them in their old logic cell numbers. So you can compare series 7 to series 6 and 5 and what have you. But they did make a change at some point. So you got to be aware of that. But the point is just looking at gross numbers. So there's 215,000 of them, of those. Okay? That's a big number. Okay. Now, maybe there's only that number divided by 1.6, but it's still a big number, right? So we're not talking about a 20 by 20 array of LUTs and flip-flops, okay? That's what we had when I started with FPGAs back in the late 80s or early 90s. The part that we used was a 20 by 20 array. You know, now they're hundreds or thousands on the side. Okay, other things to look at. There are built-in memories. And so here they're saying, well, there's 13 megabits of memory inside. And we'll talk about what that means later. There are 740 DSP slices. That's arithmetic units. He didn't talk about those.
I was just going to point out that this is max. So most of the chips we use in our classes are much smaller than this.
Pardon? Yes. Oh, yeah. Thank you for that. They're showing the biggest you can get in RTX 7. But the ones we're using in our classes on your little dev boards are way smaller than this. Good point. Okay, but you know, they're going to tell you how much performance you could get. And so, you know, lots of things they can tell you. And notice within the 7 series, they have Spartan, which is kind of their low cost, small. RTX is, well, it's what it is. But over here on the right, we have, you know, Vertex, which is way bigger, 2 million logic cells. That is a big part. Anybody got an idea what the biggest FPGA might cost?
Yeah.
Anybody knows? Throw out some numbers.
I've seen some go for $30,000.
$30,000 for a chip. Would you like to be the person who has to do something with that chip? I would stay away. I wouldn't even touch it, right? For fear if I breathe on it, static electricity will blow it up.
I had a fun experience like that at NASA. I had to burn only once Aeroflex rad hard FPGA, and it was 100K.
100K, and you programmed it, and
It's
it's
a burn once.
one-time programmables.
Yeah.
So they're unlike our FPGAs where you just keep reconfiguring. You figure it once, and if you get it wrong, 100K. Gosh, I wouldn't push the button. Okay. All right, so let's move on. We're going to really focus on a few of the features of these, okay? So I want to go to UG 474, which is a document whose title is the 7 series configurable logic block. Okay, that's a, you know, if you're interested in configurable logic inside the FPGA, this would seem to be a good document to be reading, okay? And in here, I've highlighted a few figures, and so I'll make you seasick as I scroll to them. I thought I had bookmarks, but I'm not finding my bookmarks, so we'll just have to scroll. There we go. So I wanted to show you this. So Xilinx themselves, they've coined a term called the assemble architecture. And what you can see is what these colored things are intended to show is for a given FPGA, within a given column, all of the circuitry within a given column is of the same type. The entire column will be the LUT flip-flop pair thingies, those kinds of tiles, or the entire column will be memories, or there'll be these DSP arithmetic units, or the entire column will be the interconnect channels. Remember, Dr. Godos drew in between the logic elements. He drew these wires going up and down. That's called an interconnect tile. And so the entire column will be those. And so the idea behind this is that once you find a column and it's filled and you see it has a particular kind of circuitry in it, the whole column is that way, okay? And what that means is columns don't all have to be the same width. And so even though they'll draw it where they're all the same width, who knows physically what's happening, okay? So they call that the assemble. And you say, well, that looks a little different than what Dr. Goders drew. Didn't he draw a 2-dimensional array of things? with wiring channels, horizontal and vertical. Well, you got to remember in modern processes, how many layers of metal do we have? 20? Okay, more than 20. And so all that wiring that he showed, most of that just is on top of the logic that we see. So conceptually, there's wiring in between them, both directions. But realistically, it's basically on top of it. And so the mental model I have is a little different than what's in your 220 book and what Dr. Goders drew with his 2D array with horizontal and vertical routing channels. When I'm inside Vivado looking at one of these designs, my mental model is columns of logic interspersed with columns of interconnect, realizing that the interconnect jumps up and then runs sideways over the top of the logic. Okay, so physically, how is it done? Does it look more like what Dr. Goder showed, more like what I've just described? Hard to say, okay? But in their pictures in Vivado, when you look graphically, you see columns of things with interconnect columns in between the logic. Okay, we're gonna focus on what are called CLB, combinational logic blocks, okay? Or CLB. And so what they're showing here is that in a given column, you will have multiple CLBs. Inside of a CLB, you'll have two of what are called slices. And all the stuff you care about, the LUTs, the flip-flops, they're inside the slices. And notice that the output of this slice has a carry out signal that goes up to the next tile and goes into that slice's carry in. So we're going to talk about that later because these have been optimized for arithmetic. So there's specialized structures for doing arithmetic. So we have columns of tiles. Inside of a tile will be multiple slices, okay, or sites, but in CLBs, they're called slices. And inside slices are going to be the good stuff. So let's go look inside one of these slices. They have something called a slice L, and I'm going to have to zoom out a hair. I hope you can see that well enough. Okay, so over here on the left, this slice has 4 lookup tables. Remember Dr. Goder's lookup tables? And over on the left, can you see there's 4 of them? Okay, and they have inputs. Then over on the right, you can see 4 flip-flops. So there's your LUT flip-flop pairs that Dr. Goders talked about. So a slice has 4 logic cells. What's this other gunk in the middle? Well, the early Xilinx parts had 1 flip-flop per LUT. And as he said, Dr. Goder said, and I agree, they're constantly taking user designs and looking at the contents of their users' designs that their users share with them to see, hey, if I added some extra flip-flops inside every slice, overall, would that help their circuits be smaller and run faster? Okay. And at some point in the past, between Series 4 and Series 7, I don't remember where it happened, they said, oh, we're going to add 4 more flip-flops inside a slice because that will help customer designs fit a little better and run a little faster. So you now have 8 flip-flops and 4 LUTs. What's the stuff in the yellow? Well, the stuff in the yellow is the high-speed arithmetic circuitry. Now, everybody here had 220, I assume. So you learned about a full adder. In fact, I even popped up a picture. Did I? We won't go there. You remember the full adder, you would generate a sum and a carry out from the A and the B and the carry in. This is chapter 9, figure 9.1. It's sad, I know the figure numbers. Taught the class too long. Yeah, that's called a ripple carry adder, and that's a fine adder. But they learned early on when they started making FPGAs that for many designs, the limiting factor to how fast the circuit would run is all of these carry chains in adders. That tended to be a critical path. Well, if you go take a computer arithmetic class, we used to teach one. There's been lots of ways to speed up adders. And they don't look like what you saw. What we did in class in 220 was called ripple carry. But there's things called carry propagate generate and carry look ahead and carry select. Okay, there's been a lot of ways of doing it. And so this, uh-oh,
Does that sometimes.
does it do it sometimes? Maybe I should move my mouse. Okay. The stuff in yellow is to help it do something called a carry propagate generate adder. Okay. Okay, so if you look and you say 2 muxes in an XOR gate, how in the world does that help? You'd have to go read up, but as you might guess, Xilinx has documentation on how they often implement adders. Okay, on the left side, we have all these inputs. We have a DX and we have 6 inputs to the LUT. Then we have a CX and 6 inputs to the LUT and so forth. In the lower left, can you see we have a clock enable and a set reset signal way down here. Okay. Where do those come from? Where do those signals, how do they get into the slice? Well, they come from the tile, but all the tile does is connect them to the interconnect tile that's next to the CLB tile. So the inputs to this slice come from this interconnect tile that's sitting over on the side. And then we can generate about 12 outputs. And where do they go? Well, they wrap back around and go into the interconnect tile. So those switch boxes that Dr. Goders drew, that had all the wires coming in and then all the muxes to select where the wires would go, that's all sitting to the side of this slice in what we call an interconnect tile. Okay? Now, one of the challenges, though, is to go out into that interconnect tile is a little slow. And early on, they said, hey, our speed is limited by our carry paths. And so there is a carry in, sorry, when it comes back, you can see it. If it comes, there we go. There's a carry in at the bottom and the carry in at the top. Those do not go into the interconnect tile. They're hardwired to the slice directly above and directly below it in a column. So if you build an adder, guaranteed it's going to be in a column. Low order bit of the adder will be at the bottom and the carries will propagate through this. And that can save a lot of time. And so that's a special dedicated carry interconnect to the neighboring tile. Okay. Any questions so far? It kind of looks like what we saw last time, but they grouped multiple logic cells together and they've added a bunch of other gunk to make life easy, right? Okay. Now, one of the things to notice is look in the lower left. Notice that this clock signal, each flip-flop does not get its own clock. All 8 flip-flops in this slice share that clock. That makes sort of sense. But also, there's only one set reset signal, which means if you're using a flip-flop with a built-in clear signal on it, then all of the flip-flops in the entire slice have to use that clear signal. So one of the things Vivado has to do as it's synthesizing and placing and routing your circuit is if you have various flip-flops and they are cleared on different conditions, it's going to have to figure out how to group the ones that use the same clear logic into a slice because they all have to share the set reset. Go ahead.
Can they be different polarities?
Okay, so each flip-flop can be configured to have, he will set or reset when the SR is high or low. So they have to share the same signal, but some can set a reset when it's high and some can set a reset when it's low. And also, these can be configured to have it be a synchronous reset or an asynchronous reset. So, but these are like the kind of nits that the tools have to understand to map it because they've made all these little optimizations. They could have had a separate reset for every single flip-flop, but they said, no, we're going to share them. It will take less silicon, blah, blah, blah. Okay, this is called a slice L because all it has is logic. LUTs, flip-flops, and fast carry logic up the middle, okay? But there's another guy, and he's called a slice M, okay? And slice M looks almost identical, except these LUTs look a little different. Did you see the difference? You want me to go back? I can show one of each. So here's a LUT and a slice L. And here's a LUT and a slice M, and ooh, he's got a bunch more inputs and outputs, doesn't he? So what they did is they said, a lot of designs could benefit from small memories, like little register files, memories that are 16 8-bit words or 64, 16-bit words. So they added some logic in the slice M to the LUT. So you can either use it as a normal LUT, or one of its configuration properties is to use it as a memory. Okay? And so if you look at this guy, he has a data in, he has some lines that are marked A6 through A1. Well, that could be the inputs to the LUT. But we've also got W6 to W1. Are those write addresses? Yep. Okay, there's a write enable, okay? And so this can be used, this can be configured and turned into a little teeny memory. Instead of a piece of logic lookup table, you can use it as a little teeny memory, okay? And when you want little memories, this is a great way to go. The other thing that can happen though is this MC31, this can be configured as a shift register, a variable length shift register, okay? And we'll get to that in a minute. So that's slice L, slice M. And so when you see a CLBLL tile, it means it has two slice L's in it. You'll also see CLBLM tiles. It means it has a slice L and it has a slice M in it. Now, the beauty is the tools know how to map, right? The tools, you write your Verilog code, the tools figure out what to use, but the purpose of today is to help you get a feel for what might be inside. So it's just not this magical black box, because let's face it, in 220, it was, if I write my system Verilog code the way the professor said and the way the textbook showed and push a button, magic happens and the lights blink the way they're supposed to, right? And we're trying to get you beyond that, okay? We're trying to get you to have a little deeper understanding. All right. Dr. Goders talked about a LUT could be used as, here we have a 6-input LUT right here. But notice it has 2 outputs. Do you remember what he talked about last time? Remember you had this tree of muxes making the LUT? And he said, well, if you back up, you can peel off 2 of the intermediate signals and treat it as 2 5-input LUTs. Do you remember that? The Xilinx word for that is fracturable LUT. And these are fracturable LUTs, so it can be configured. You don't see it here because the configuration, those are bits that aren't shown in this picture, but you can configure it as 2 5-input LUTs. And here's the 2 outputs of the 2 5-input LUTs. But of course, you've only got 6 inputs to the LUT. So just as he said last time, they have to share the same inputs to be able to be used, right? You can't have 2 arbitrary 5-input LUTs with their own 5 inputs. They have to share inputs. Okay, so these are fracturable LUTs. Okay, all right. The last thing I want to point out is, see if I can draw a box around it to make them stand out. There are 3 gray muxes that I've just circled in red. Can you see them? Right here? Well, look, if you remember, Dr. Goders drew a LUT as being built as a tree of muxes, right? Well, look, we have some more tree of muxes. And so you can take 2 of the 6-input LUTs, and using that mux, you can turn it into a 7-input LUT. Okay? You can do that with this, or you can take all 4 of them, and using all 3 muxes, you can turn it into an 8-input LUT for certain functions. Okay, so they've added these as well. So that's everything in the picture, I think. Okay.
And the names of the muxes are?
F7 and F8 mux. Okay. So, yeah, that kind of helps you understand function 7, function 8. Okay. Any questions so far? That's kind of what's inside the block. Yeah.
I know that you said you'll get to this later, but you said that there's a configurable shift register. Can you get at that by just making a shift in your Verilog code?
We're just about to start to talk about that. Okay, how do you design to take advantage of this stuff? In 220, you prove to yourself that you can write arbitrary system Verilog code and magically it gets mapped as. What if you really know you want to use a shift register, but you don't want to use 64 flip-flops. You want to take advantage of the shift register that's built into the slice M. Okay, well, it turns out that they talk about
Next tab over.
there he is. Okay, so they have a document. Oh gosh, it's 600 pages long. Okay, the Vivado Design Suite Libraries Guide. So they have built a library of building blocks that represent all of the little circuit things you can map onto those boxes. Okay, and so if you want to know how to use one of the boxes in that picture, this is a great place to go look. For example, let's go to the FDRE. Okay, it's a primitive D flip-flop with a clock enable and a synchronous reset. And there's a picture. Okay, yeah, look, we got a D, a clock enable, a clock, a Q, and we got this R. And you come down below and they give a little logic table and look what it says. It says if the clock enable is 0, right here, then it doesn't matter what the D and the C are on the clock edge, nothing's going to happen. That's what clock enable means, right? Okay. On the other hand, if the clock enable is a 1, well, then whatever appears on the D input will appear on the Q output on a rising edge of the clock. Okay, of course, that all presupposes that reset was low. So they tell you how the primitive works. Okay, and then they say, can you instantiate that primitive right in your Verilog code like any other module? And the answer is yes. Can you get it inferred? And that's kind of what Ben was asking about. And they say recommended. In other words, don't go and write, well, in fact, here, let's look. They show how to instantiate it. Here's our Verilog instantiation right here in gray. Okay, right? You can say instantiate an FDRE. By the way, it has a parameter. I can tell it whether I want on power up the thing to initialize to a 0 or to a 1. And then I can map my signals to the ports. Well, as we learned in class, it's a terrible way to design, right? You want to write things like always FF at pause edge clock, Q gets D right there, right? And then Vivado synthesis tool sees that. It's an idiom that it recognizes and says, I can map that to one of these flip-flops. Now they have a lot of flip-flop primitives, okay? If you were to write this code right here, okay, always FF, if clock enable, then if R, Q gets 0, else Q gets D, it will map that right onto an FDRE for you. And so when it says inference recommended, it means, yeah, don't be instantiating individual flip-flops. But Vivado can infer them, okay? So we'll get to your specific question, but that's a start, Ben, right? Okay. So if this should give you a hint though, if you can learn how to write your shift register code in the right way, then the synthesis tool will recognize it and will go grab an SRL shift register primitive to use. If you write it the wrong way, he might build it out of 64 flip-flops, which isn't what you want. So part of this libraries guide, for a lot of these, they actually tell you how to write your behavioral code so that the synthesis tool recognizes it as one of the primitives, which is kind of funny, right? You can write it in this high-level code, but you have to write it in a very specific way or the synthesizer won't recognize it. Okay, I want to talk a little bit. We're going to talk about lot RAMs. We're going to talk about SRLs, which are shift registers. And we're going to start to pick up speed. We're going to talk about carry logic, we're gonna talk about VRAM, we're gonna talk about Waka managers, okay? So these are just some of the things that are in the design. So let's go to, we're gonna go back to our CLB, okay? And we're gonna go to page 28. Okay, and here we go. As promised, you can use one of the lots in a slice M as a RAM. Now it has six inputs, and those will be the address lines. So how many locations are in the RAM with 6 inputs? What's 2 to the 6th? 64, right? So this is going to be a 64 by 1 bit RAM. And look what you do. You configure it to be a RAM instead of a LUT. That's a configuration parameter that you can set when you instance it, or Bravado will set. You've got a single bit of data in. You've got a single bit of data out. You've got 6 address lines, and they're going to double as both the read and the write addresses, because there's technically only one set of address lines on this guy. They're the LUT inputs when it's programmed as a LUT. You got a clock and a write enable. So you can apply data, you can apply an address, you can apply the write enable, and on the clock edge, this will store the bit you want. Okay. And this RAM is asynchronously read, meaning you don't have to wait for a clock. If you change the address lines after a combination logic delay, the output will change. Okay. Or do we have lots of flip-flops in the slice? Yeah, there's 8 of them, right? And so if the code you write has a synchronous read, meaning I want to see the data after the clock edge, you'll just grab one of the flip-flops sitting there. So this is nice because you can have either asynchronous or synchronous reading. And here's one where you can say, oh, but I really want a dual port. I want to be able to write and read independently. I don't want the read and write addresses to tie together. So what do? Well, notice that the address that's being used for the write address here is also being used for the write address on the LUT below it. So when you write to both copies of the memory. Okay. And when you read, okay, whatever address is on write here, that's what you'll read from, but he has his own read signal. So they call that dual port. Okay. It looks like a 64 by 1 memory. It has 2 sets of address lines. Okay. You can read using both sets of address lines, but if you want to write, you can only write using the top set. Okay. All right. So you get the idea, and they go through a boatload. Here's a 4-port quad port memory with 1 write port and 4 read ports. So they're all configurable, so the tools know how to cobble these together in any size and shape of memory that you desire. And we call this LUT RAM because it's being built using the LUTs in the slices. Okay. The next thing we want to look at is page 34 is where the SRLs, and we can answer Ben's questions. So the picture I like is this one right here, which says, well, this is the LUT, but he's now been configured to act like a shift register. We can shift data in, and 32 cycles later, that data will shift out. However, we do have a bunches of addresses going into this LUT. They're the LUT inputs, right? So we can actually select which of the 32-bit positions we want to look at. So if we tap off here, we have a 32-bit shift register. But if we tap off here, we can choose how long of a shift register it is, and we can change how long of a shift register it is on every clock cycle. This is a little weird. Ever heard of a shift register with a dynamic length, right? But that's a possibility. So if you wanted a 43 length shift register, what would you do? You put in a 32-bit shift register, and the shift out would become the shift in of another shift register, but then you would put the number 11 on the address lines of the second shift register, and the sum total would be 32 plus 11. And so what would come out of the second guy would be a 43 cycle delay of what came in this guy. So you can string them together and get arbitrary size shift registers. Does that make sense? Now, Ben, your question is, how do you write it? You could instantiate these SRL primitives, and the document we were looking at would tell you how to do it. But the document will also say, and if you write your code a particular way, you mentioned the arrow operator. Yeah, that might be good enough, but they'll tell you how to write it so it'll recognize it. Now, in 220, we often said, go read the synthesis report. In fact, we made you go read the synthesis report and tell us what the circuit used. When you start using these kinds of features and you're writing and you say, did I code it in a way the synthesizer recognized it as a shift register? Now you're going to want to definitely go look at the synthesis report and make sure if you're expecting 5 shift registers in your design, that it says, I inferred 5 shift registers. And if it doesn't, you might want to go look at your coding style and figure out what you did wrong.
Are the tools open enough that you can go in and see
Yes.
the specific one?
Yeah. And right at the end, we're going to pry open Vivado and start looking around inside. Okay. All right, so we've done shift registers, LUT RAMs. Is there anything else we want to talk about? We've talked about the carry logic. I want to talk about 2 other things, then we're going to fire up Vivado. Inside your design, in those columns, some columns can be memory elements. Okay. We call them block RAMs in Xilinx terminology. Intel has a different name for it, but they also have memories. You all agree you can build a memory out of flip-flops, right? Sure. Flip-flops and gates, you can build a memory, but it's very inefficient. And so if you know you want 32 kilobits of memory with a custom piece of silicon, they can make a much smaller memory than you could ever build out of flip-flops and gates. So they have dedicated parts of the FPGA to contain these specialized memory blocks called VRAMs. Okay. And we're very quickly, I'm going to show you the basic primitive, and you can read more about it. So they have a primitive and it holds 36 kilobits of storage. You say, that is a weird number. Doesn't everything come in powers of 2? Well, they decided they wanted this memory to have the ability to have data bits and parity bits. And you know about parity for error correction? So if you look up top, there's 32 bits of data in, and there's 4 bits of data in parity. Okay, so that's where you come up with the 36. It really looks and feels like 2 separate memories, one 32 kilobits, one 4 kilobits. Okay, now it's dual ported. So you have address for port A, write enable for port A, an overall enable for port A, et cetera, et cetera. You have a clock for port A. And those are all independent from the same signals for port B. This is weird. I could be writing and reading from the memory using this port at 100 megahertz, and I could be writing, reading from this port at 165 megahertz. It's one common storage of 36 kilobits. That's kind of cool. Now, what happens if you are reading and writing from the same location on different clock edges? You might get some weird behavior, so you're going to have to think about it, but it supports that. Okay. Now, we got 36 kilobits, yet we have 32 data. Okay, let's ignore parity for a minute, okay? Ignore the parity half. We got a 32 kilobit memory array. We have 32 data lines, but we have 16 address lines. Well, 16 address lines implies what? What's 2 to the 16? 65,000, right? 64K. So that many address lines implies there's 64 kilowords in here, which is more than the 32 kilobytes that we get. But also, well, you can't have 64 kilowords and have them all be 32 bits wide. So what in the heck is going on? Well, what's happening is these are the ports on it, but the memory itself is configurable. You can configure it to be 1K words of 32 bits each. Does that give you 32 kilobits? Yep. You can configure it to be 512 words of 64 bits wide each. You can configure it to be 32 kilo words of 1 bit wide each, which means if you were to instantiate this and give it the appropriate parameters to make it 32K by 1, a big, tall, skinny memory, well, 31 of those data bits are going to get ignored, aren't they? So you're going to have to put a bunch of zeros and then the data bit you want in the right-hand bit. So this sort of is the maximum number of bits you can wire up, but you're going to have to wire up constants to fill it, okay? But still, you have this weirdness of this can address 64 kilo locations, yet there's 32K words maximum. Well, these can be cascaded together. And I have always assumed that's the discrepancy. Now, you can instantiate one of these and it would take a full page of Verilog code because it has so many parameters associated with it. The better way to go is to do what we did in 220. Okay, and I do have that up. Remember our little register file we had in chapter 19? Some of you may remember this, okay? Well, and then we showed how to code something, okay? Let's see. Let's do the bigger memory. That was right. Larger memory. Here we go. Okay, so I've said, well, I want 1024 by 4 bits. So 1K words, 4 bits each. Always FF pos edge clock. If reg write enable, you know, we write into the location being addressed by the address, but always on the positive edge of the clock, the output is whatever the address is addressing. Okay, that will be mapped to a block RAM. And notice I didn't have to worry about the cascading. I didn't have to worry about, well, which of those sizes and shapes of the BRAM do I want to configure that? And I don't have to worry about zero padding my address and data lines. I just write what I want and the synthesizer is smart enough to choose. Oh, with this, well, let's see, it's 1K by 4. That will easily fit. I think I will configure this as 1K by 32. And I will just put zeros in for 28 of the data bits, right? Both on read and write, because you're only going to use 4 bits worth. And so the synthesizer will choose that for you. Now, if this had been 1K by, oh, let's say 64. Well, that's too much for one memory. So the synthesizer is smart enough to use 2 memories and play some games with multiplexing on both the inputs and the outputs to treat it as a bigger memory. I have seen cases where it will tile out an 8 by 16 array of these block RAMs to make a very large memory that's wider and deeper than one little memory can do. Okay, you get the idea? There's a whole column of these in your FPGA. So those are block RAMs. Finally, let's talk a little bit about I/O. Okay. So in your code, you can instance something called an OBUF. And the input or the signal in your FPGA can go through a buffer and it drives it out to a pad, which is then tied to the metal pin on the chip package, which then goes into the printed circuit board. Okay, but you can also do what we call an OBUF, and you, whoops, that was iBuff. Sorry, whoops, I'm sorry, I misspoke. I don't know why. I had bookmarks. I had bookmarks everywhere here, and they're gone, so I'm having to scroll. Okay, the OBUF, yes, the OBUF goes from inside the FPGA outside. Well, there's an iBuff that goes the other direction. What I want to show you, though, is up at the top. They were all bookmarked. This is embarrassing, guys. Here we go. Here's an example of an I/O cell. So let's look at it. This is the wire that goes to the chip package, the outside world right here, okay? The pad, okay? Now notice, if you just want to come in, you can come from the pad and you can go into this buffer right here, and that will then come into the circuit. But what are these other signals? We got 3 other signals coming into the buffer. For a dumbbell input, they aren't used, but can you see that you can disable that buffer with this signal? Okay, and the tools will have to tie that low if you don't want to disable it, right? But if your design needs it, there it is. We learned about tri-state in just last semester at 220, but in general, we don't. But that's another thing. And so you got a tri-state control. And you've also got something called a diffie-in, meaning, you ever heard of differential I/O, where it takes 2 wires? And it's a 1 or a 0, not because one signal is high or low, but because it's a little higher or lower than its twin brother. Okay, that's called differential I/O. Why would you use differential? What's better about differential?
It's more stable depending on your cable length and things.
Okay, you're not worried about DC offsets and all those problems. Okay, all you care about is the difference between the 2 wires' voltages, which makes it immune to transient noise effects and all kinds of things. So for high speed, so you can gang up 2 of these and do differential, which is a cool thing. Okay, now if you want to drive out to the pad, we got this guy here, and same thing. We have a disable. We have a tri-state, but you can take a signal in the FPGA and drive it out to the pad. So the synthesizer takes care of configuring all those things for you. And those are the IOs that are, they used to be around the periphery of the chip. Now they're in columns in the middle of the design as well. Okay, as promised, let's fire up a little bit of Vivado and just start poking around, okay? So I have Vivado running here. So after you synthesize and implement your design, there is a button called Open Implemented Design right there. Can you see it? Right here. Nope, down here. Okay, near the bottom. Okay, once you have implemented it, you can now open it and you can see the physical design. You can see how things were spread around the FPGA by the tools. And if you do much in terms of low level, you spend hours inside this interface examining how things got mapped and where the wires go and blah, blah, blah. So let's just go inside and take a look. So what I did is I just jumped down in, and I think what I'm going to do is I'm going to grab, let's grab these 2. Okay, so what are we looking at here? Well, what we're looking at is, here is a CLB on the right. I'm sorry, guys, in Zoom. I'm pointing to the right half of the screen. Okay, there's 2 slices. Can you see 2 structures here? In fact, you might be able to read the name, slice something and slice something. So that's the CLB right there. And sitting right next to him is what we call an int tile. And I think this is an int R. Okay. And so the inputs all come in from the int. They go into the slice. If you look carefully, can you see 4 LUTs where my mouse is? Some carry logic. The 4 intermediate flip-flops and the 4 final flip-flops. The inputs are coming from the left, from the interconnect tile, and the outputs are wrapping around and going back out to the interconnect tile. Do you see that? Okay. So if we zoom in a little bit, let's just take a look here and see. Does this look like our picture? Well, it looks a lot like our picture. I'm sorry, that's a little faint for you guys, isn't it? It looks better on the screen. Okay, we got LUTs, we got carry logic, we've got bunches of flip-flops here, we've got muxes, etc. Okay, now if we zoom back out a little bit, what we can do is we can grab a signal. Okay, that signal wasn't very interesting. Let's go grab a different one. Okay, I'm going to grab that signal. So as we can see, the signal that I've highlighted, it comes out of one of the flip-flops. Okay, he has a name. Okay, he's called CLBLM_M_DMUX. That's the name of the wire. Okay, it's the DMUX output of the M slice in the CLBLM. Okay, and where does it go? It goes around back to here. There's a little bit of programmable routing right here, and then those run out and they run into the interconnect. Okay, let's go into the interconnect and just look at something. See if I can make it work here. Okay, there you go. Do you see all that? What is all that? You remember Dr. Goder showed, let's see, this is an output. See how the arrows are leaving where my mouse is and they're going everywhere? Okay, if you were to follow those are all of the places that this wire can go. And on the other end of that wire is, you would find the mux that he showed. So for an output, you see all the places the wire can go. Now, can I find an input? I think I have to page up. Okay, here we go. I go, is that an input? Nope. Yeah, these are inputs. Okay. So let's just do a quick count. What do we see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, there's about 18 inputs into that wire. So what really is happening is there's a mux. All those wires are converging on a mux that we haven't drawn. And in Xilinx terminology, you call each of these connections, if I can select one, maybe if I select, okay. So each of these connections is called a PIP, programmable interconnect point. So if I zoom out, let's see where that particular wire, okay, so can you see that a wire coming in here, there is a connection through the mux here, okay. Come on, can I get it to stay? It's very temperamental, there we go, okay. And you can see all the other places the wires come from. Look on the right-hand side. Do you see some wires coming out and turning around and coming back in the dingle? Those are called bounce pips. It's because you need the ability to go to a particular wire, but instead of leaving, just turn right around and re-enter and go somewhere else. Because remember, Dr. Goder said, not every wire can be connected to every other wire. So if you come in on a wire here and you get over here to go into a LUT and you can't get there because there's not a connection, you might go to one of these bounce pips who itself has a connection. And so sometimes you'll see your signals go into the switch box and bounce around a couple of times before they exit on the correct wire. Okay, so those are called pips. So when you look at a placed and routed design, I believe this is a placed and routed design, but it's teeny. There's almost nothing in it. Let's see, is this something to look at? I can't tell. That's what we were looking at. No, that's not it. I don't have a good design here. Oh, here we go. This is a really dumb little design. Okay. As you can see, I think I have two signals coming in, coming over here, going through a LUT and going around. I think this is a 2-input AND gate, if I'm not mistaken. So not a very interesting design, but you can see that the green lines are the actual signals in your circuit. Should we see what they're called? He's called F_OBUF. So I guess he's the output, right? We often use F for outputs. How about this guy? No, I want the wire. Give me the wire. No, maybe I'm just going to have to zoom in a little better. There we go. Okay, so that's B IBUF, and I'll bet you this is A IBUF. Okay, yep, so I have A and B coming in from these two pins on the left. They're running to the right, okay? And I don't know why it goes so far, but it goes all the way over here, okay? It brings them in to a LUT. The LUT ANDs them together, and it sends the signal back out, okay? And that leaves the slice, and then if we zoom out, it goes all the way back over to the IO pads where it's an output. So there's a 2-input AND gate implemented in an FPGA. How many of you have done this level of playing around inside Vivado? Okay. Yeah, the people who I recognize have been involved in research for a while, and those of you who are newer, you very possibly will. Okay. All right, so we're out of time. But there's one more thing I want to talk about. There are some things that you just cannot infer. Okay? Some things that you cannot infer, and you have to go to the documentation to figure out how to instantiate them. Anybody have an idea what an example would be? How about clocking? So, all of our designs we do in our classes, most of them are pretty simple, aren't they? Bring in that 100 megahertz clock. Everything in the system runs off 100 megahertz. Life is good. In a real design, you might have 3 or 4 clocks at different frequencies running. And you might care about the phase relationship of those clocks. For example, you might have a 100 megahertz clock coming in. You might want to have a 50 megahertz clock, but you want the 50 and the 100 to be in phase, meaning when the 50 megahertz clock is going high, so is the 100 megahertz clock. Okay. That may be important to you in the timing of your design. So they have something called multi-mode clock managers. So what this picture is trying to show is embedded in the FPGA are dedicated columns and rows for clocking. So this is called a clocking backbone. These 2 columns, there's a clock backbone, etc. And then you have horizontal clock rows, and then your logic lives in these little clock regions in between. Okay, so the idea is, if you're going to run at maximum speed, you just can't bring in a clock on an arbitrary pin, run it through programmable routing to all the flip-flops in the design, and expect a design that has any hope of working. If you take 620 from Dr. Worthland, I believe he talks about clock skew. The idea is you want every flip-flop in the entire circuit to see the clock edge as close to the same instant in time as possible. Because if you have 2 flip-flops and one of them sees the clock edge half a nanosecond before the other, can you see how that might cause problems? What if the output of this flip-flop goes to the second flip-flop and the second flip-flop gets the clock late? Might he load the wrong value? He might. Or what if the roles were reversed? The second flip-flop gets the clock early before this guy. Well, now he gets the clock, but his input he's supposed to act on doesn't arrive until late. So this idea of the flip-flops all being clocked at the same time is crucial. And so hidden from us is a huge infrastructure that can have like 16 clocks all running around at different frequencies, but every wire length and every driver has been carefully calibrated to get every flip-flop in the entire circuit to get the clock edge as close to the same instant in time as possible. And if you ever run a detailed timing report, they will build in a little thing called clock skew or jitter. And that is the uncertainty of when various flip-flops receive their clock. To control all this, to give you your different clocks, they have something called an MMCM. And this is where the analog stuff comes in. You bring in your clock, okay? You have, what's this called? You have something called a phase frequency detector. Okay, he detects whether the incoming clock and this reference clock coming out of the feedback are out of phase. If they're out of phase, he generates an analog signal to something called a charge pump. Okay, the charge pump, he outputs something which goes into what I believe is called the loop filter that goes into the voltage controlled oscillator. And what this little string of things is doing is it's trying to take your input clock and line it up with something else in phase and then multiply it by a factor of like 8. Now, if you can take a 100 megahertz clock and multiply it up to 800 megahertz, now do you see that you can divide it down and get other frequencies? How do you get 80 megahertz from 100? You multiply 8 and then you divide by 10. And that's what this circuitry is doing. And so from a single clock, you can get 100 megahertz, 80 megahertz, 133 megahertz, 25 megahertz. And not only that, you can program these output stages to carefully control where the phases of those clocks are. Okay. But you don't write behavioral system Verilog and have one of these pop out. You have to get in here, you have to read the documentation, and you have to learn how to instantiate one of these clock guys. It's an advanced topic, but if you're going to do high performance, important design, it's one of the things you have to learn. But of course, to make it easy, what does Xilinx provide? A clock wizard, where you go in and you say, my input is this frequency, and I want these output frequencies, and here's what I want for the phases. And it does all the magic and outputs the instantiation for you. And if you play with that very long, you learn some weird things. If you have a 100 megahertz input clock and you say, I want an 80 megahertz output clock and a 60 megahertz output clock, it might come back and say, well, I can give you 80 and 61.7, but I can't give you 80 and 60. And it has to do with the ratios as it multiplies up the frequency and divides it back down. And you learn how to tinker with it until you get the one that's important to be exact, because the others might not be exact. Or you just use a second clock, multi-mode clock manager, MMCM, and you take the 80 from the one, and now you do something to it to get you the 60. So more advanced stuff. So the deeper you go, there's a lot of stuff. And good designers and people who are doing this commercially and who are putting it into products, they're wringing every bit of performance they can out of the part by understanding more at the level we're talking about today. Okay. So that's all I have, and we've gone over by 5.
Just a few comments on for the clock wizard, you can also do a manual override, so you can play around with the different dividers, multipliers. Exactly. Calculate it all for you, which is kind of nice.
Very nice.
And also in Vivado, there is a language template on the left, on the flow navigator near the top. There's a language template, and it will show you, you can just search any primitive and it will show you how to implement the primitive. And
okay. See, I've never used that button. I always go to the document I showed you and copy and paste their Verilog.
It does like the primitives, the XTC file. It also does like interfaces. If you want to implement an interface in the block diagram and stuff like that.
Here, let's do it. We're here. How do you show us where? This is something I have never used. I've just.
So yeah, it just.
It's good we're done, because I'll be out of
Language templates up there in the under project manager.
There we go. Language templates. Okay.
Search, just hit the magnifying glass and you can just search the primitive and it gives you examples.
Okay. Oops. How about SRL? There you go. Here's how you get a 16-bit with clock enable shift register. And there's
It's also, you see, it's for every architecture. So it has,
Arctic 7 will be different than, Kintex Ultra Scale and blah, blah, blah. So that's kind of cool. Thank you. That's good.
yeah, and there's too many tools.
Oh, there's so many things in here. Okay, I hope this was helpful. I hope it gives you a little more look under the hood. Don't be shy. Everybody goes through it. The moving from 220 level magic to, oh, I understand what's inside. That's a hard jump. And you may spend your whole graduate career, or at least undergraduate and part of your graduate career, feeling comfortable with that. But as you can see, there's a lot here. Okay. Thanks, guys.